Welcome to this lesson on the error in Taylor polynomial approximations. Okay, so remember, this is a Taylor series. We take a function, we choose a point A, and we represent the function as a polynomial, or sorry, as an infinite series of polynomial terms that are centered around that point A. And that's the important point, right, is that the series goes on forever, right? Goes up to infinite number of terms. In practice, what we usually do is go up to some finite degree. I'm going to call it capital N, and we throw away all the higher degree stuff. Like, we're going to use a quadratic approximation to the function, we're going to use a quintic approximation, and so on. And once you throw away other terms, you can't have an equal sign anymore. If you just throw away other terms, you're only approximating. Another thing you can think about is you can keep your equal sign, and you can only go up to a finite number of terms if you're willing to write down the error term, right? This error term represents all the stuff you throw away in your Taylor series that's higher than degree n. So first, let's parse through this. X minus a to the n plus 1, where the capital N is the highest degree in your Taylor polynomial. So if you wrote down a third degree Taylor polynomial, this is x minus a to the fourth power. Okay, this is n plus 1 factorial. This is the n plus first derivative of the function, not evaluated at a, but evaluated at Greek letter xi, which is somewhere between x and a. And you don't know what it is. So this is kind of strange, but this error is exactly right for some value of xi that's in between your value a, where you expanded your series, and x, which is where you might be constructing an approximation, like where you might be evaluating your Taylor polynomial. So even though we can't know the value of xi, there's a theorem that says that this is the right form for the error term. It's in your book. The proof of it, reading it in the book is as elucidating as me going through it here, so I'm not going to do it, but I want you to know how to use this error term. And even though we don't have an exact value of xi, since we know what range it's in practice, what we try to do is bound the error term, right? So we're going to say the error, we usually look at the absolute value of the difference between the true value of the function and the polynomial approximation, and we take the absolute value of that difference and we say what's the furthest apart these things could be. More specifically, here's the original function, here's the nth degree Taylor polynomial approximation, here's the error term. This is kind of just rewriting what was on the previous page. I'm going to move the Taylor polynomial approximation over to the left-hand side. I'm going to take the absolute value of each side. And so this says, what's the distance between the real function and your Taylor polynomial approximation at some point x? It's equal to this thing. Since we don't know xi, what we do is we do the worst case scenario, which is we choose xi to make this whole thing on the right be as big as possible. So it's like a maximal distance between these two things. And what we then come up with is some statement like the distance between f of x and the Taylor approximation is less than or equal to some maximal error. So this is called bounding the error term. And here's how it works. We'll just do a little example. Let's bound the error in the second degree Taylor polynomial approximation for cosine of 0.7, where we construct our Taylor series around x equals 0. So first, let's figure out what the polynomial approximation is. Cosine x around 0, we know off the top of our heads. It's 1 minus x squared over 2 factorial. And I'm using the approximate sign because I've only kept two terms here. So you can plug in 0.7 for x, and you'll find that cosine of 0.7 is approximately equal to 0.755. Now we're going to write down the error term. And since we wrote down a second degree polynomial, the error term is going to be the third derivative of the function evaluated at x equals xi, divided by 3 factorial, times x minus a to the third power. And our x is 0.7, our a is 0. And xi is some number in between those things, where we don't know what it is. okay? But now we can ask, what's the worst case scenario? What makes this thing in absolute value bars be the biggest, right? Because this is just some number, this is just some number, this is the thing we have to bound, and we know that cosine x, cosine is a function that goes between that goes between -1 and 1. So a really easy bound on the absolute value of this thing is just 1. Cosine is never bigger than 1, okay? And that happens when xi is equal to 0. So if you choose that worst case scenario, you have 1 over 6 times 0.7 cubed. The minus sign doesn't matter because we're taking absolute value, and that turns out to equal 0.057 and some more decimal places. So putting it all together, we come up with a statement that says the true value of cosine of 0.7 minus our Taylor polynomial approximation value, which was 0.755, is less than or equal to this value. Like, we're guaranteed that we're no worse than 0.0571667 in that guess. We can actually compute the actual error, because we can just take our calculator and punch up cosine of 0.7. The actual error turns out to be much smaller than this error bound, but that's fine. Now, a word about convergence. Okay, in a previous lesson, you've used the ratio test to assess whether a Taylor series converges. But even if we show that a Taylor series converges, that doesn't prove that it actually converges to the thing we want it to, which is our original function, right? And a way that we can try to get at that is to show that the error goes to 0 as n, capital N, goes to infinity. Meaning, as we take more and more terms in a Taylor series or Taylor polynomial approximation, the leftover bit, the error, can we show that it goes to 0? And let's just do it for what we did above. We'll take the function cosine x around 0, and here's the Taylor polynomial out to some degree n, and here's the error term. And since the function is cosine, we know that this term, the term with the xi in it, is bounded between -1 and 1. So the worst case in absolute value is that the numerator here is equal to 1. Let's take that worst case, and what we're left looking at is what is the limit as n goes to infinity of this error term? How big is this error term as we keep more and more terms in the polynomial approximation? That's the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial. Well, this thing grows way more slowly than this thing. Factorial gets big really quickly. You might be familiar with that fact. If you're not, you can plot it. You can ask me about it in person if you have the opportunity. But the limit of this thing as n goes to infinity is 0. So the fact that the error goes to 0 is telling you that the series not only is going to converge, but it actually tells you it converges to the correct function. Okay, thanks for listening.